number 7. And also I want to show you something new for the t-distribution, because they added some features in Excel for right and left-tailed testing, which will make that part of the homework easier. So I want to show you guys that as well. So I'm just going to go ahead here and share my screen. All right, so let me show you guys first how to do number 7. All right, so this problem asks us, this is very similar to question 6. So we're going to do this in a similar way, except in question 6, they actually told us the claim in mathematical as a mathematical formula. So we had the claim. So this gives us mu, our alpha level, our standard deviation, our X bar, and our N. So we're going to do this the same way, except now we have to pull all this information out from the problem. So we have to look in the problem for all this information. And then this one does have us do it a little bit differently, because I think this one, number 6, had us use a p-value, and number 7 has us use a critical value. So I want to show you guys how those are related by, I'm actually going to draw it for you so you can see how those are related. Okay, so so when we look at this problem, homework 4.3, number 7. All right, so when we look at this problem, it says a light bulb manufacturer guarantees the mean life of a certain type of light bulb is at least 752 hours. So I'm just going to type some notes in here. So the claim is that the mean, which is mu, is at least 752. Okay, and then it says a random sample of 26 light bulbs. So that tells me that sample of 26 has mean of 730. Okay, so a sample of 26 has a mean of 730 hours. Assume the population is normal and the standard deviation is, so they told us it's normal, and that the standard deviation is 3. And they tell us that alpha is 0.2. Okay, so they gave us that. And then it says, do you have enough evidence to reject the claim? So the first thing is, we're going to start with this. The claim is the mean is at least 72 hours. So at least is greater than or equal to. So this includes, so this claim is mu greater than or, oops, I'll put it in less than, greater than or equal to 752. So that's what the claim is. Okay, and then it says we have a sample of 26. So this tells me that N is 26 and the mean is 730. So that's my X bar, because that's my mean of my sample. So X bar is 730. And then the standard deviation is 63. So that is my S is 63. Oh, population deviation. So this is sigma. You need to pay more attention. Okay, so it said the population standard deviation is 63. So what we need to run the test, we need mu sigma X bar and N. And then this is our claim, and it has a greater than or equal to. So that means that this is my null hypothesis. So my null hypothesis is this. I'm just going to copy this because I don't want to retype it. That mu is greater than or equal to 752. Since it has the greater or the equal to sign, this is the claim or the null hypothesis. And then I like to write in that this is my claim. And then my alternative hypothesis is the opposite of that. So it's mu strictly less than 752. So that's the first thing it asks us for. So that's this one here. Mu greater than or equal to 752 is the claim. Okay, and then it wants us to identify the critical value. Okay, so before I do that, let me go ahead and fill these things in. So my mu is the one under the null hypothesis. So it's this, the 752. And sigma is 63. And X bar is 730, and that's that population mean, or sorry, sample mean. This is the sample mean, and then the N is 26. Okay, and then when it asks for the critical value, so this is the probability, or sorry, we set the probability equal to the alpha level and the critical value. So whenever it asks you this, and they call it Z naught, so this is always based on the alpha level. So the critical value is the Z score or Z value for alpha. So basically, this is the one that you would like. You would look up the alpha level. So for whenever they ask you for this, you're going to use norm.inv, and you're going to put in for your probability, your alpha level. Actually, it's standard normal, so we're going to use norm.s. Okay. So let's start by finding Z naught. And it is norm.s.inv. So I just use my arrow to go down to that, and then I can use my tab to grab that. And so just remember, we use norm.dist if we want to get back a probability. And we use norm.inv if we have a probability and we want to get back a z-score. So here we're going to use norm.s.inv, and then we're going to put in our alpha level. So I'm just going to click on that. And that's the only thing that goes into this is the probability. And that is negative 2.05375. And then we just want to check, because this tells me whether I have a right-tailed, left-tailed, or two-tailed test. It's always based on the alpha level. And since this is less than, I wanted to show you guys what that looks like. I'm just going to draw a picture. Where's my little thing to draw? No, it's so weird. Usually it gives me a little thing right here so I can grab a pen.
You might have to click on those double arrows above the pointer and below the ellipsis. Oh, sorry.
Yeah, they're not working. Oh, there we go. Thank you.
No
All right, there's my pen. So I just wanted to show you that the reason it's a left-tailed test, so mean is actually 752. Or sorry, our mean was 730. And what this is saying, we're claiming that the mean is greater than 752, and we base this on the alternative. Okay, it's like this seems really weird to me. But it would be out here. But when we're checking the alpha level, I shouldn't have drawn that. Back here. When we look at this Z naught, I guess that's why I couldn't see that, because I made my thing so short. If it's a right tail test and our alpha level, this is standard normal, so this is 0, and our alpha level is 0.02. So if I have a left-tailed test, then it's out here, the 0.02, and this is alpha. Okay, and this gives me that Z naught. So when I use that norm.inv and I put in the 0.02, what I get is the Z naught that corresponds to a left-tailed test. And if it's a right-tailed test, so this is left-tailed. If it's a right-tailed test, you guys have to forgive my terrible drawings of bell-shaped curves, but then my Z naught would be over here if it's right-tailed, and then this would be my alpha equals 0.02. And so here you would want to use, here you're going to get a negative critical value. Is negative, and over here you're going to get positive. And this Z naught is the critical value. So it's the one, the critical value is the one based on the alpha level. And then if it's two-tailed, what happens is we split it in half. And so if alpha is 0.02, we have 0.01 in this tail and 0.01 in this tail. And you end up with two critical values because your rejection region is split in between these two tails. So you get a negative Z naught and a positive Z naught, basically. But when you look it up, you look up 0.01 and it'll return the negative value. So you just want to also use that for this one, and this one is for two-tailed. So I just wanted to kind of show you how that works, because I think it makes more sense when you see it. So this, again, is what the critical value is telling me. And then what happens when I calculate my test statistic, if this is also my rejection region. So if I calculate a test statistic, which is the Z that you calculate using x bar minus mu divided by sigma over the square root of n, if that calculated value for a left-tailed test is out here, then I'm going to reject the null hypothesis. And if it's in here, this is, I'm not going to reject. So the rejection region is this really small region. And if it's right-tailed, it's the same thing. And when you calculate the p-value, what you're calculating is the probability from the table that you get a value, if it's left-tailed, that you're getting a value less than that test statistic that you calculated, which is why if your test statistic is in this rejection region, which means it's less than Z naught, that your p-value will also be less than alpha. So just wanted you to know those tests return the same results. So you can either look to see if the critical value falls in the rejection region or if the p-value is less than alpha, because if the critical value is in this rejection region, then naturally the p-value will be less than alpha, because anything out here will have a probability that's less than 0.02. And anything over here, the probability that the value is less than what any number over here, that probability is going to be greater than 0.02. So they give you the same answer, and that's the relationship between them. All right, so let's go back to this. So the first thing is identifying the critical value, and that is the value using the alpha level. You could also look it up in a table, but they want you to use technology. So when they ask for this, the table might give you a different answer. And then it says round to 2 decimal places. And I like to use the little formatting thing. Usually shows up for me. Where is it? Usually shows up like in here. And I tell you, I'm just having nothing but issues today. Yeah, here we go. Usually it shows up, and this will change my decimal places. So I like to use that and just format it to the right number of decimal places, because when you format it to 2 decimal places, it automatically does the rounding for you. This is negative 2.05. Okay, and again, if that was a right tail test, this would be positive. Right, and then it says identify the rejection region. So that's what I was just showing you. So what they didn't show us here when they drew this, so because this is a, oh, I thought I wrote down what it was. So because this is left, then this is a left tail test. Okay, if this was greater than, then this would be a right tail test. And if this was not equal, it would be a 2 tail test. So because it's a left tail test, and what they didn't show us is what that kind of means. Okay. So I'm going to just draw it again. So it's left tailed. So it looks like this. This area over here is 0.02. And this Z naught, we calculated it, and it was negative 2.05. And this is 0. So when they draw this, and this is where we would reject H naught, they didn't put that value in here, but you can see 1, 2, that it's marked at negative 2.05, but they didn't write it on the graph. So I just wanted you to know that this does match this. So that's what this is saying. This rejection region, we're going to reject H naught if we get a calculated test statistic that falls in this region out here, which is less than negative 2.05. So this is the one for the left-tailed test. Okay, and then it says identify the standardized test statistic. So that's the one that we calculate. So we just call that one Z. Okay, and that is the standardized test statistic. And so it equals, oh, let me write the formula out here. This, the way we calculate this is Z equals X bar minus mu divided by sigma over the square root of n. That's how we calculate it. So when we put that in, note equals parentheses, and then it's X bar minus mu divided by sigma divided by the square root of n. Okay. And then this is nice. It shows me the colors. X bar blue minus mu red divided by sigma purple over the square root of n green. It should look like that. Okay, and that gives me negative 1.78. I think they also wanted that to 2 decimal places. Okay, and then it says decide what to do. So you can calculate the p-value, but we can also just look, and negative 1.78 is over here. It's greater than negative 1.25. I'm just going to draw a little arrow up to that. That would be negative 1.78, and this is the do not reject. Out here and over here is my reject. So this is do not reject H naught. So it falls in the do not reject. So we fail to reject H naught. And whenever we fail to reject, it means that there is not evidence. So there is not evidence to reject the claim. And you can look at your little table to see that. And then I also wanted to show you that we could also calculate a p-value for this so that you could see that the p-value is actually going to be greater than 0.02. So if we want to calculate a p-value, we do that using norm.s.dist. And we put in this, since it's left-tailed, we just put in this z value, true. We had to put true, yeah. And the p-value is 0.037, and that is greater than 0.02. Oops, I must have marked it wrong. Oh, I marked reject instead of failed reject. It's just looking at the wording. We fail to reject because there is not evidence to reject the claim. All right, and then I also wanted to show you guys